we talked about a peculiar function called the distance function, right?
Yeah.
And it's often called a metric. So the word metric is used in many places. Here it is used in the form of a distance function. There are certain properties of this distance function. So if x is a space, which is in this case, what I have in mind is a topological space. I'll explain what that is. So if x is a space, and if you take 2 points from this space, as I was saying, that if you take any 2 points in the space, then you can compute something called the distance between those 2 points, the distance between those 2 points. And there is a formula to actually calculate the distance, whatever your formula, your favorite formula is, and that will give you a real number, a non-negative real number. And I will give you an example of such a function d, such a distance function d. There is a very simple example. We all know about this. Suppose x is R2. R2 means the xy plane. You can think of it like that, or you can think of it as a set containing duplets such that both x and y are members of real numbers. So that's what R2 is. It is without any additional structure at this point. Now you can take a point A and B, which are members of R2, A and B, which are members of R2. So for example, you could take A is equal to 2 comma 3, B is equal to 5 comma 6, and so on. And now you can define a function, a distance function, in the following way. You can say, okay, the distance between A and B is simply square root of 2 minus 5 whole square plus 3 minus 6 whole square. Okay, so this is the familiar Euclidean geometry that we all know, right? We all know about it. This formula is known as an Euclidean formula. So if A is equal to x1 y1 and B is equal to x2 y2, then distance between A and B is square root of x1 minus x2 whole square plus y1 minus y2 whole square, right? So this is known as the D Euclidean, or it's a Euclidean metric. Euclidean metric. But last day we talked about different another metric, a different metric, right? Another formula, D taxicab. This is A comma B. So do you remember the formula? If the input is
Yeah.
still x1 y1 and x2 y2, what was the formula?
Modulus of x1 minus x2 plus modulus of y1 minus y2.
Modulus of x1 minus x2 plus modulus of y1 minus y2. So this is known as the taxicab metric. The taxicab metric. And the reason it is known as the taxicab metric is because of the way you are actually moving along the plane, right? If you are in the point A, which is 2 comma 3, and if you want to go to a point B, which is 5 comma 6, the taxicab metric tells you go along the grid lines. You are only allowed to walk horizontally or walk vertically, right? So in this case, the formula is 5 minus 2 absolute value plus 6 minus 3 absolute value, which is 3 plus 3, which is 6. And there was some very interesting thing that we observed in the last session, that the circle looks
Becomes a
very
square.
different. Yeah, so this is a circle. Okay. So what is the circle in the taxicab metric? As you mentioned, in the taxicab metric, this particular picture is the picture of a circle. It's quite fun actually. This object right here is by definition a circle in the taxicab metric because all of these points are equidistant. So this is 1. This point is half comma half. So that is also 1 because you go one half unit here, half unit here, total is 1. So this is what a circle would look like if your underlying metric is a taxicab metric. So this is something that we discussed in the last class. Now we said that the reason one of the reason one can do topology is the following, that when you change the metric, we see that shapes get deformed. Right. A circle doesn't look like a circle anymore. It gets deformed and looks like a square, a traditional square. So that way the geometry changes. The geometry changes. But then certain things will not change. Certain things will not change about the underlying space. And one of the things that does not change, and we have already talked about, is the number of holes
Holes.
in the plane. So if you start with a plane with R2 with no points removed, if you start with a hole in R2 with no points removed, you will continue to have a plane no matter how you change R2, how you change the underlying metric, you will still have no holes. Okay. So that is one of the things that sort of lets us go beyond geometry. We go beyond geometry. So that's one of the reasons people study topology. Now, did you get a chance? So topology tells us what does not change if we change the metric, the underlying metric. Okay. So that is a viewpoint. That is a viewpoint that we are extremely interested to understand because the underlying space is something that we want to study, not only the shapes that we can draw on it. Okay, properties of the shapes and so on, shows the space and so on. Another thing that is kind of intriguing if you think about it, one of the reasons people study, one of the things that people see when they look into geometry is the notion of functions. So when we study functions, can you tell me, Anushka, one of the definitions of a function that you know? Maybe you can, yeah.
It's a relation in which one element is only mapped to one element, not multiple elements.
Okay,
One in domain.
okay, that is great. So, so there are two sets. This is a domain, and then we have a codomain, right? And the function is a map, is a relation, is a one-on-one correspond is a correspondence which relates elements on the left hand set with the elements on the right hand set. And you actually told me a rule that one element in the left hand set cannot be corresponded to two elements on the right hand set. That is one of the reasons people one of the definitions of functions. That's absolutely right. Now you see, the great things about functions, if you think very closely about it, it tells you how to move from one set to another. You have elements in one set and you want to move from one set to another, and somehow then this other set's elements have the information of the elements in the first set hidden inside them. Hidden inside them. The map sort of takes the elements and they can absorb it inside that one element in the right hand set. So that is one of the ways of thinking about functions. Now in topology, we want to study certain functions called continuous maps. So are you familiar with the definition of a continuous maps
Not
or
exactly.
continuous function? Maybe you have read about continuous function in
Yeah,
calculus.
yeah, there are no breaks in it when we plot the graph.
When we plot the graph, there are not any sort of breaks in it. That's true.
Or a
That
hole if we
or a
take in.
whole, yeah. That is definitely true. That's one way we think about continuous maps. When we Can you give me an example of a continuous map, of a map that is continuous everywhere, continuous only at one point and discontinuous everywhere?
Sure. Um, Continuous at exactly one point and discontinuous everywhere.
Yes.
Okay, so we can take that as um,
So this is
maybe a point function. Like
yeah. Sorry.
if we take a point function, then that will be no.
Point function. Hmm. Okay, so this is a very standard type of question. If you are interested in the interviews of Ivy Leagues or I don't know Oxford, Cambridge, or whatever, this is a standard question that sometimes people are interested in. You know, you want to know about, because the traditional thinking about continuity, that we don't have any breaks, that is actually not how should be thinking about it. And these are counter examples to those kind of thoughts. So uh, why don't you find out a map that is continuous at only one point and discontinuous everywhere else. So there are famous examples of this sort of functions. There are very standard famous examples of this sort of functions. Okay, can you hear me? Hello, Anushka.
Yeah, I can hear you.
You can. I don't know, my computer sort of froze. Just a second. Yeah, now I can hear you again. Yeah. So now the thing is that we will now think about continuity in a very different way using tools of topology, because we want to make the transition from regular geometry or calculus or whatever to a more general concept of topology, right? That's what we want to do. So let's try that. Let's try that. So I'll come back to the notion of topology, the notion of topology in this manner that so we start with a set. What is a topology? What is a topology? So we have a set X which we start with. Our example was R2. We can have another example. We can have another example which is R1. That's fine as well. R1 means all the real numbers. But that is just a set. This is just a set. Now we put some structure on this set. We define something called a topology on X. So what is a topology? A topology is simply a collection of subsets of X. A collection of good subsets of X. Now when is a subset good? So when is a subset good? What makes a subset good? Well, really, there is no one answer. It's just that we want certain properties from this collection of subsets. And if those properties are satisfied, then we will say T, the members of T, which are nothing but subsets of X, those are good subsets. Why are they good? By virtue of being inside T. Now, what are the desired properties of T? Well, there are only a few, three, four properties actually. That empty set is inside T, the entire set is inside T. If A1, A2 up to AN, finitely many subset members of T are finitely many members of T, then their intersection, that is A1 intersection A2 intersection up to AN, is also inside T. And moreover, there is a distinction that we want in the fourth case. A1, A2, AN up to, you can go up to infinitely many members. If they are members of T, then their union is also a member of T. So you can do finitely many, you can take finitely many members of T and you can take their intersection, because members of T are after all subsets of X, the underlying set. So you take the intersection, what you get is another member of T. So we say that's how the collection T is created, to include all of these things. And if you take infinitely many members of T, then their union will also be a member of T. So these are the properties that we desire from the collection T. If the collection T has all of these four properties, we call T a topology on X. Okay. So I'll
ठीक है.
give you an example. I'll give you an example. Suppose our space X is only these three elements A, B, C. Because after all, X is a set. Now let's build a topology on X. So firstly, we want phi, then the empty set. Secondly, we want the entire set ABC. And thirdly, whatever we put, we want the union of that to be inside ABC and the intersection as well. So suppose I can put A, B. Is this a topology? Suppose if I put singleton set A, singleton set B, and maybe I put AC. Is this collection T a topology on X?
Yeah, it is.
Okay, think a little bit about it. Does it have all the desired properties?
Um, all the no, it is not. A and B. A B should be there.
AB should be there, isn't it? Okay. So is it now a topology if I put AB in there?
Yeah.
It is a topology, right? X is the underlying set and T is the topology on X with all the desired properties. So this is how you can handcraft a topology given a set. It's not complicated at all. It's very simple. It's just a collection of subsets of X such that the collection has a desirable property. The collection has entire set, the phi, the empty set, the and the finitely many intersection is in the set. In possibly infinite unions are also in the set. So all of these four properties are there. Okay, great. So we have an example. Now let's go to a more important example. Real numbers are. So we know that it's a set of numbers like 0, 0.1, 1, like this, -3, and all these numbers are there, right? We want to define a so this is the underlying set. This is the underlying set. Now we want to define a topology on R. Now there are various ways of doing it. We can define a topology on, because whatever collection we take, or collection of subsets of R we take, if we have, if that collection has the desired properties, then that collection will define a topology on R. So one of the, this is the standard topology, standard Euclidean topology. Standard Euclidean topology is generated by open intervals. So basically, what I'm going to write is not the topology, but it's the generator of the topology. So you take a set B, which is also a collection of subsets, which contains AB, where A and B are in real number. So all intervals, all finite intervals or infinite intervals are in this, finite intervals are in this particular set. So 2 comma 3 is in this set. 2 comma 3 interval means all the points between 2 and 3, right? All the numbers between 2 and 3. So one can define a topology, Euclidean topology on R using these open intervals. So what you do is you take union of members of B. I mean, you can take arbitrary union, you can take finitely many and take their union, you can take infinitely many and take their union, whatever it is. When you do that, you get a collection of subsets, which is obviously bigger than B. This is known as the basis, and then you get the topology using that basis. Okay, so this is one example of a topology that you can put on the real number set. There are many other examples of topologies that you can put on the real number set. So I can give you a little homework. Try to find out some topologies on the real number set. Find some other topologies on R. Okay. All right. So now the question is that why are we interested in these uh, in topology? Well, one of the reason is that we are interested in continuous functions. So continuous function. So what is the definition of a continuous function? What is a continuous function? So this is the new definition. It's not, so this is the new definition. It's not the calculus definition. This is the topology definition. Okay. So suppose we have a topological space X Tx and Y Ty is another topological space. So what do I mean by X Tx? Well, can you tell me, can you guess what is X and what is Tx? Well, I cannot hear you actually.
X will be sort of the domain, and like TX, no, not like that, but
What is
TX is the topology defined on X.
Tx is the topology defined on X, topology on X, and X is the underlying set, right?
Yeah,
X is the underlying set, and Tx is a collection of subsets of X with those desired properties. Similarly, Y is another underlying set, and Ty is a topology on Y. Ty is a topology on Y. Correct? So
yeah,
we understand what it is. Now we define a map from X to Y. Let's call it F. So it is a set map. First of all, it's a set map. It is associating members of X with the members of Y. That's what it is doing. Now we want to know whether this set map is a continuous map or not. What is the meaning of continuous maps? Well, it's very simple. What we do is, suppose this is Y and this is X. We first look at good subsets of Y. Good subsets of Y. Can you tell me, Anushka, what is the meaning of a good subset of Y?
it lies in TY.
Exactly. So some subset that so this is a good subset of Y if this subset is a member of Ty, the topology. Very nice. So we look at the preimage of good subsets in here. So basically all the points in X that maps to that good subset in Y. Let's call this good subset V, and let's call this one U. And we ask the question, is the pre-image of a good subset good? So that means, is U in Tx? That is the question. It will obviously depend on the function f.
Yeah,
What's going on? But if this happens, if for every good subset in Y, the preimage of a good subset is a good subset of X, obviously X has a different topology, then we say that the map is a continuous map. So if this happens, if yes, for all good subsets of Y, so for all good subsets of Y, the pre-image of the good subset is good. If this happens, then F is continuous. So why are we interested? Again, let's come back to this. what are the examples of continuous map? One type of example of a continuous map, and you can easily show this, are isometries. Example are isometries. For example, can you give me examples of isometries in Euclidean plane, Anushka? Distance preserving maps. Maps. So if you have a distance function defined on R2, and suppose it's a Euclidean distance,
Shifting it,
yeah.
like if you shift it all, then it will be an isometry.
Okay, shifting. So that's a translation is an isometry. Yes. You just move it. That's an isometry. What else is an isometry?
If we rotate it,
Rotation is an isometry. Excellent. So all of the motions that we have studied in geometry so far, these are actually isometries. In fact, when you look at homothety or when you look at inversion, that is things where their shapes are changing, even then we can say that those are also isometries, but those are hyperbolic isometries in the sense that the underlying set and the metric are different. So that is heavily studied in other parts of mathematics. That is, you change the underlying set and you change the underlying metric, and homothety inversion are isometries of that particular set and with that particular metric. So these are called hyperbolic isometry. Now the point is, Anushka, that these isometries are also they also happen to be continuous maps. Isometries are actually examples of continuous maps. They are very good examples, in fact. So isometries are, in fact, very good examples of continuous maps. And you can easily sort of visualize it. If you have an interval, like a ray, and if you say R, suppose you have R, and if you take an interval on R, let's say 2 comma 3, open interval, and if you shift it by 5 units, you go to 7 comma, I don't know, 7 comma 8, right? This is an isometry. You parallelly shifted it. But remember, if you this is a good subset of R because it's an open interval. Remember the Euclidean topology we put on R. The preimage of this open subset under this translation map is 2 comma 3, this open subset, which is also a good subset. So this translation is in fact continuous. So you will notice that all of these maps, rotation, translation, homothety, inversion, depending on what topology and what underlying set you are using, those are isometries, and those are examples, very good examples of continuous maps. Now think about it like this. If you understand the properties of continuous maps, those properties will be applicable to isometries as well. Because after all, isometries are continuous maps. Not all continuous maps are isometries. Of course, that's not true. But if you study continuous maps in general and figure out certain properties of all continuous maps, then certainly those properties will be applicable to the isometries. So one of the reasons people study topology is to understand the properties of continuous maps. And why? And you were saying that how can we go from geometry to topology? So Indirectly, while studying the properties of continuous maps, we are also studying the properties of isometries, which are objects of geometry, right? So I told you two things in these 2 days of discussion. The first thing that I told you, that there is a metric. Changing the metric changes certain things, but you want to know what are the metric independent features of the underlying set. Features of underlying set. Hence, you go for the topology. And second thing I told you is to study the properties of continuous maps, which are then indirectly applicable to isometries as well, which are objects of geometry. So these are the connections that you are expected to understand, or you can think about and have fun with, because after all, we are doing all of this for fun, right? We want to enjoy it. So any questions, Anushka, so far?
No questions.
No questions so far. Okay. Okay, these are interesting discussions. We are looking at transitions from geometry to topology. Um, you can look into the homework problem that I gave you. Think about it, okay?
Yeah.
And if I can, I will meet you again in a couple of days again. All right. All
Okay.
right. Take care. Bye.